Okay, so let's talk about generalization and some practical issues like how do you choose this nonlinear feature transform. Okay, so first of all, just to summarize, in your X space, you have X is in 1 cross R to the D, okay, and in your Z space, Z is in 1 cross R to the D tilde. Okay. Now, if you ran a linear model in this space, your VC dimension dVC would be, equal to D plus 1, and you prove this. Now, there's no difference. You've just taken your data, okay, and just, bloated or shrunk the number of dimensions, maybe kept them the same. Okay, so your new number of dimensions is D tilde. Okay, so your VC dimension here, dVC, let's call it dVC tilde, is equal to D tilde plus 1. Okay, and it's the same theory. It's the linear model. It's the perceptron. So we have control. So the error bar, so E out, will be less equal to E in for G. Okay, plus order of the square root of D tilde over N log N. Okay, so because it's the linear model, but in a higher dimensional space, you have the link between E in and E out, and the error bar is related to the dimension of this space. Okay, and that raises the question, so what should you pick for the dimension of that space? Okay, so what should D tilde be? Okay. And the obvious answer is go to the lowest dimension space that you can while still getting E in, let's say, close to 0. Why? Because if you're in the lowest dimension space D tilde that you can, now you've got an E in close to 0, okay, and you've got the tightest link that you could possibly have asked for if you've gone to the lowest possible D tilde. Okay, so choose D tilde small gives better E in, E out approximately equal to E in. Okay, so smaller D tilde accomplishes the first step of learning more efficiently. Okay, and this leads us to the issue of, well, picking D tilde amounts to picking the nonlinear transform. And in general, there are many ways to pick the nonlinear transform. So in general, there are many ways to pick phi. And, what's illustrated here, okay, so, we have our data, okay, and let's get some red and blue markers. Okay, so we have our data with, blues, okay, and reds around, okay, and that's the top graph over there, okay, and, the first transform that goes down, which basically goes to Z1 equals X1 squared, Z2 equals X2 squared. That's the one we've been discussing all along. And on the left, we show another transform, which is, just take Z2 equals X2, Z1 equals X1 plus, that's something like 0.6 squared. Okay, and, this guy succeeds in separating the data by putting the, the reds on one side and the blues on the other side here. Okay. And this transform succeeds in separating the data by putting the reds sort of on the right and the blues on the left. Okay? And so in both cases, here you can separate with this line, here you can separate with this line. And as you can see, there are many different feature transforms that one could choose, which accomplish the goal of getting E in small, and we want to choose the one with the smallest dVC tilde. Okay, so now, when you think about it and you look at this data and you say, well, that's, interesting, because, here's a circle, and it turns out that the equation of this circle is x1 squared plus x2 squared equals 6. Okay, so what about if I just take my data? So what about if I define a feature transform to one dimension? Okay, just one dimension where, my one dimension Z1 is equal to x1 squared plus x2 squared minus 6. So literally, if this is 0, okay, it takes all my blue points and takes them to less than 0, because this is less, in this region you're less than this value. Okay, so when you compute x1 squared plus x2 squared minus 6, you'll be less than 0. So all your blue points will be around here, and your red points, they are going to be around here, And look, I've got perfect separability in one dimension. Okay. And so, we can get now E in close to 0 and a DVC of just 1. Okay, one feature, one DVC of just, actually DVC is 2. That's the tightest possible link we could ask for with respect to linear models. Okay, and at this point, I'm going to say, I smell a rat. Okay, and it's very important for me to pause the video, or for you to pause the video and figure out whether you smell that same rat. It's a very smelly rat, and it's very important that you smell that same rat and sort of figure out in your mind, you cannot do this. Okay, and why can't you do this? You can't do this because, you're not allowed to look at the data before you pick your feature transform. And, all of these sort of scenarios, which are are saying things like, there's this way to choose the feature transform, there's this way, but there's this optimal way to that one dimension. Those are all based on sort of looking at the data and saying, oh, there's a circle. You're not allowed to look at the data. Fundamental. You cannot choose your feature transform after you look at the data. You have to choose your feature transform before. Okay? And so let's discuss how you can actually use the feature transform in practice, because isn't the feature transform supposed to get you E in close to 0? Okay? So using the feature transform. Now, okay, so choosing the nonlinear feature transform, you have to choose the nonlinear feature transform before you see the data. So you must choose the nonlinear feature transform phi before you see the data. Okay, that's very important. But then you might ask, well, how do I even know I need a nonlinear feature transform if I don't get to look at the data? So this is where you have to sit down and think about the problem. So you sit down, you say, okay, I've worked hard, I've incorporated saturation, I've constructed the right features, but, it could still be that, even though I've constructed income, maybe it's income squared that is important. Or, I've got age, but maybe it's age or the square root of age that's important. Okay, so you're thinking that even though I have my features, I'd like to put in a little bit of added flexibility with some basically additional features that I get by transforming my original features maybe to the same original features plus a few more. That's an example of a feature transform that, strictly speaking, strictly adds features. Okay, so this is how you decide what's the nonlinear feature transform you're going to do. You have to think about the problem and say, are my features enough, or do I need more flexibility to manipulate those features, maybe multiply them together and so on and so forth. But then you come to the issue of, well, okay, so I need more flexibility. Then I have to sit down and think forever and ever and ever. Well, yes, that's ideal, but you could also instead just use some standard feature transforms that exist in practice. Okay, and the most standard of the feature transforms is the polynomial transform. Okay.